All right, welcome. So this is lecture 18 of Chemistry 106. I believe when we met before, we discussed this problem here. This was a fairly straightforward problem. This is a problem I would hope that you could solve fairly easily. We had started to solve this problem, which is a little bit more involved. We're told that in excess of silver chloride, that means we're going to have some of this salt at the bottom of our beaker at the end of the reaction. In any case, in excess of this material is added to now a solution. In the past, what we've seen is we've seen salts added to pure water. Here we're adding it to a solution of sodium chloride. And the question is, what will be the final concentrations of the silver 1 ion and the chloride ion? And of course, you should know how a salt like this dissociates based on what you learned in Chem 105. And so we have a few instructions on solving this kind of problem. These instructions won't be given on an exam. Actually, let me make this go full screen. These types of instructions probably wouldn't be given in an exam, so you'd probably you would need to know how to do this. So the first step, when I have one salt and yet another salt in solution, is to consider the dissociation of the completely soluble salt. So it's going to fully dissociate, and I believe, as we discussed before, and you should be able to see that if I have 1 molar sodium chloride, what I really mean here is that the concentration of sodium ion is equal to the concentration of chloride ion, which is equal to 1 molar. So again, this is kind of a Chem 105 type thing, is you should be able to recognize that we have complete dissociation of this salt. Therefore, again, these concentrations are equal. So we first consider this dissociation, and now what we're doing is we're taking some silver chloride and we're dumping a small amount of this into this solution right here. So these ions are already present, they're solvated, they're swimming around in solution when we dump the silver chloride in. And now what we're going to do is we're going to set up a problem in which we use the equilibrium constant, the KSP value, for the silver chloride. So even though these other ions are present, this equilibrium still has to be operative. So what we can do is we can write down silver chloride, and again we've got the solid form of this salt is in equilibrium with the silver 1 ion plus Cl minus. And we can set up an ice table. An ice table is a good place to start. Again, it's the old Ray Gilbert thing from my high school days. If you don't know what to do, do something. And we see we've got a KSP problem. We've got some initial conditions. So we might as well put down what we have initially. Let's just at least try using an ice table. So initially, well, at the instant when we drop the silver chloride into the solution, we have some silver chloride. At that same instant, none of the silver chloride has dissociated, so we don't have any of the silver present. And then we've got a 1 molar concentration of chloride ion. And so I think that these are fair initial conditions. Again, the moment that this is dropped into this solution right here, this is what I'm dealing with. And you say, what about the sodium? And the answer is the sodium ion is a spectator. That 1 molar sodium, those sodium cations just sit there, they do nothing. They certainly aren't having any impact on this equilibrium. And again, this equilibrium, as written, needs to be operative. So the next question is, are we at equilibrium? And we've discussed this multiple times. Equilibrium means that I have a forward reaction taking place at the same time I have a back reaction taking place. So I look at these concentrations and I say with a concentration at 0, I can't have any back reaction taking place. It doesn't mean that a huge amount of material is being transferred from this state to this state and vice versa, but I do have to have a forward reaction and a back reaction at equilibrium. And so again, if my silver ion concentration is 0, I can't possibly be at equilibrium. This tells us the direction that equilibrium has to go. The reaction has to go forward to create some silver ion, so that then I can have this dynamic equilibrium of the reaction going forward and the reaction going back. And so that means, again, because this is 0, we have to have some material dissociate as the change here. So initially we had some of this dumped into the solution, now some dissociates, and I'm going to get an amount plus X here, and I'm going to get an amount 1 plus x here. So if some of this dissociates, every time one of these dissociates, one of these is created and one of these is created. You remember our corny example where we had the dance and we had a couple turning into a boy plus a girl. So you know the dissociation of a couple yielded a boy and a girl. A boy and a girl come together to form a couple, and so it's the same thing down here. When silver chloride dissociates, I get one silver. I get an amount x of silver and an amount x of chloride, and so then because we were told that we have an excess of silver chloride, in my equilibrium state, I have some of the silver chloride left, which means I have a chance for equilibrium. If I have some of this and some of these, I could possibly be at equilibrium. I have an amount x here, and I have an amount 1 plus x. And now we're going to do something that's going to be quite important in this class. And what we're going to do is we're going to consider the magnitude of this number and what the size of x must be. This, and the question I always ask the class is this a large or a small number? And you all say it's a small number. Of course it is. It's on the order of 10 to the minus 10. So the KSP value is a tiny number. And so what does that tell you about the dissociation of silver chloride? Is a lot going to dissociate, or will only a very small amount dissociate? And as we saw in the previous slide, in the previous lecture, when I have such a small KSP value, only a small amount of silver chloride will dissociate because this number is so small. And so what that tells me is that x will be a small number. Again, this is a tiny number. Remember what we said, when you solve these problems, what you want to look at, and one of the first things you look at, is the size of the KSP value. Here KSP is really tiny. That tells us this reaction is not going very strongly to the right. In fact, it's hardly going to the right at all. So very, very little dissociation of this material. X is going to be very, very small. 1 molar concentration is actually quite large for Cl-. And so what that means is that we expect x to be very small compared to 1. In other words, let's see, we could write over here, kind of like this, we can say that x is much, much less than 1. And if x is much smaller than 1, then it's often a very good approximation mathematically, and it will indeed make our math much simpler, to simply neglect x. And now I can write, so mathematically I'm neglecting it. I'm neglecting it because of this right here. Again, I'm neglecting x because it's so much smaller than 1. I neglect it because of comparison. I can't neglect this x, and that's always one of the questions I get. Well, if you're neglecting this x, why can't you neglect this x? And the answer is because I'm not comparing this x to anything. It just stands by itself. Whereas I'm saying I'm taking this and I'm adding x to it. It's like if I had $1 billion and then we added a penny to it. And in fact, it's probably going to be, you know, on that order of magnitude. You've got $1 billion and you're adding a penny, and you say the penny is just not very significant. Whatever calculations I do, the $1 billion is going to matter, not the penny. And so that's why, based on the KSP, we're saying we expect x to be really small. Here's the $1 billion, here's the penny. We're just going to forget about the penny in our calculations, and we expect the calculations to come out pretty good because, again, a penny just doesn't affect $1 billion very much. So we're going to write down KSP is equal to, and let's see, we're going to leave off the concentration of the silver chloride because it's constant, it's a pure solid. So the KSP is equal to the concentration of the silver ion times the concentration of the chloride ion. And now that we've neglected x, now that we've said this is something on the order of a penny versus $1 billion, $1 billion, this is so small it's insignificant. So now things get easy. We're saying that, let's see, x has a concentration, silver has a concentration of x, and chloride has a concentration of 1 molar. And then our KSP value is 1.8 times 10 to the minus 10, and we can see immediately that the 1 goes away, and we're just left with x, which is the concentration of silver ion, is equal to 1.8 times 10 to the minus 10 molar. And so now my question to you is, did we make a good approximation? Is x really truly small compared to 1? And the answer is yeah. I mean, this really is the difference between about $1 billion and 1 penny. the 1 penny truly is insignificant compared to the $1 billion. Again, I can't neglect this x because I wasn't comparing it to anything. It was, there again, it's just a number by itself. But this number compared to this number, this is certainly negligible. So this looks like this is our solution to the problem, and this is the concentration of the silver ion. What's the concentration of the chloride ion? We were asked for that. Well, the chloride ion was equal to 1 plus x. We neglected x, and you know what? This is a really good approximation. Let me put the decimal point in there. The chloride ion really basically is just 1 molar. It's not going to be a change. This is not a change in concentration that I can detect. This is so many significant figures out here. Just tons of numbers out here. I don't even have that many significant figures in the problem to worry about this. So this truly is negligible compared to this. The last thing that we need to emphasize here is that any time we neglect x, and we're going to neglect x in subsequent problems, we should always check to make sure that x really is small compared to 1. And the criterion that we establish for this class, and you could establish different thresholds or whatever. What we're going to say is that if x is less than 5%, if this number is less than 5% of this number doesn't have to be 1. It could have been 2.5 or 0.8 or whatever. But as long as this is less than 5% of that, then we say we made a good approximation. So how would we test that? We could take, in this case, this number divided by this number, so it's x divided by 1. I'm going to multiply this by 5%. No, I'm sorry. I apologize. I'm probably going to make a few mistakes. I hope to catch them. I am a little bit jet lagged here. But I'm going to take x and multiply it by 100%. And the question is this going to be equal to or less than 5%? And we can see that it is. If I put in 1.8 times 10 to the minus 10, then this becomes, so I put this number in right here, this becomes 1.8 times 10 to the minus 8%. And again, how did I get to this? I just took this number, put it in here because I'm comparing this to this, and I've got 1.8 times 10 to the minus 8%, which is certainly much, much less than 5%. In other words, we made a good approximation. And this is how we solve the problem, and I think that that's going to be the answer. Yep, these are the answers right here, so the concentration of silver and the concentration of chloride. And again, we're going to play this game over and over as we solve this problem because we're going to be dealing with differences in concentrations that are enormous. So it makes sense from a practical point of view to neglect x, but also if you think hard about it mathematically, and I won't test you on this, but if you think about the number of significant figures that would be necessary for me to add 1 to this. See, look, I've only got 2 significant figures here. It makes no sense to add in 0.000000 and then get 1.00000018 or something like that. I don't have enough significant figures in the problem for what's clear out here to make any difference over here. I've got uncertainty at this point. When I have 2 significant figures, that means there's a little bit of uncertainty in this decimal place. If there's uncertainty here, does this number matter at all compared to this if there's uncertainty here? And the answer is no. And so not only is it a convenience, but I'm strongly justified mathematically to neglect x, but I do it by comparison again. It's always by comparison. Is this less than 5% of this number? Okay, probably enough said on this. Next question. We've got some excess calcium fluoride, small KSP value, placed at the bottom of a beaker of water. What is the equilibrium concentration of F minus at equilibrium? Now, we look at this problem, we say, okay, we're taking this salt, we're putting it in water. There aren't any other ions there in solution to compete or to compare to, so this problem is probably going to be fairly straightforward, like the penultimate problem, the kind of the last problem we completed in the last lecture. But let's see, we've got calcium fluoride, and let's write its dissociation. So I've got Ca2 plus 2F minus, and again, we should all know how to do this based on Chem 105. Okay, so, and I put an excess, I'm just going to write excess, so I've got a whole bunch of this as my initial condition. I drop this again into water. At that instant, there's no calcium 2 ion that's in solution. There's no fluoride in solution. but I can't possibly be at equilibrium for the reasons we've discussed. Equilibrium means that reactions are going both ways. There's nothing to react here. So there must be a change, and so we have some dissolves again. And so that means I get plus x here, but I get plus 2x here. And we see this from the stoichiometry. Every time one of these units dissociates, I get one calcium, but for every one calcium that one calcium 2 plus that's created in solution, I get 2 fluorides. And then I come to equilibrium, so initial change equilibrium, and I was told I had an excess of this material, so I have some left. And I end up with an amount x here and an amount 2x here. So those are my concentrations. Now we're asked for the equilibrium concentration of F minus of the fluoride ion. So let's set up this problem. Let's see, we have KSP is equal to, so tiny number 1.5 times 10 to the minus 10. And this is equal to what? Try to make that a better 0. This is equal to x times 2x quantity squared. And I do a little bit of algebra here, and I see that this is 4x cubed. And so let's see, this means that x is equal to, again, if I'm working off of this, and this right here, I guess we could work off of this. So we have 1.5 times 10 to the minus 10 divided by 4. So that takes care of the 4. Now I'll take the cube root of this, and now I've solved for x. And so let's throw this in our calculator. I have 1.5 times 10 to the minus 10, really small number right here. I divide by 4. I take a cube root, and I'm left with 3.3 times 10 to the minus 4 molar. But there's a potential pitfall here that you should watch for, and that is that in this problem right here, we solved for x, and x is the concentration of the calcium ion. We were asked for the concentration of the fluoride ion here, and this concentration, the concentration of the fluoride ion is going to be twice as great as the concentration of the calcium ion. Again, this just makes sense. If one of these dissociates, for every one of these, I get 2 of these. So this means the concentration of fluoride I have finally in solution is going to be twice as great as the concentration of the calcium ion that I started with. So if this x right here is the concentration of the calcium ion, and it is, then we can see that if we multiply this by 2, we get the concentration of fluoride in solution. And what's listed here is the concentrations of these species, not 2 times the concentration. This is the rule that tells us how the dissociation takes place. What we're listing here is the actual concentration of the calcium here, the actual concentration of the fluoride here. This is the amount of the calcium fluoride here. So that's something that can be a little bit tricky as well, and you have to keep this in mind. This is the rule telling you how this dissociates. Well, okay, so again, calcium fluoride, let's see, it dissociates. So for every calcium fluoride unit, I get 1 calcium and I get 2 fluorides. But this right here, this table is telling me the actual concentrations of the calcium, and it's telling me the concentration of the fluoride, not 2 times the fluoride. This is just the concentration of the fluoride. So this is the concentration of the calcium, twice that is the concentration of the fluoride. I think we have enough said, but in any case, I take twice this, and that's the concentration of the fluoride, or it should be, and yes, that is the correct answer. Next question. So this now is going to be back to being a little bit more tricky as a problem. And again, you should master this type of problem that we're dealing with. These will show up on the next midterm. They will certainly show up on the final. And there will be a couple of problems like this in both cases. And so it really behooves you to understand how to do this. Okay, so the KSP for magnesium hydroxide is a small number. Now we have an excess of magnesium hydroxide placed at the bottom of a beaker of 1.5 molar sodium hydroxide. Okay, from Chem 105 we know that sodium salts are soluble in water, and so that means that initially in this solution, this sodium hydroxide solution, we have concentrations of sodium and hydroxide of 1.5 molar. Alrighty. And we also mentioned that the first thing that we do when we solve these problems when we have two salts. And do I have two salts? I do. Let's see, I have sodium hydroxide, and this is a soluble salt, and I have magnesium hydroxide, which is the insoluble salt. So we learned when we have two salts together, let's take care of the dissociation of the soluble salt first. It makes a lot of sense. It completely dissociates. So, we have 1.5 molar sodium hydroxide units, and that really means, of course, since this completely dissociates, it completely breaks apart. I have a sodium ion concentration equal to a hydroxide ion concentration of 1.5 molar. Now that we've taken care of this, let's deal with the addition of this sparingly soluble salt to the solution of this other salt. And so I'm going to write down now the equilibrium expression for magnesium hydroxide. So let's see, we've got magnesium hydroxide, we've got Mg2 plus 2OH minus. And let's see, we're told that we have an excess, so we have lots. We can be very vague in designating the amount of magnesium hydroxide that we have. We have an ice table that we're setting up because we certainly have initial conditions, then we're going to have a change, and we're going to come to equilibrium eventually. But let's see, what do we know? We know that the concentration of hydroxide is 1.5 molar. And remember that what's put in this table right here is the actual concentration of hydroxide. The 2 is just part of the rule. It says that one of these units, we could put a little S here if we wanted, and an AQ here and an AQ here. I won't write those in. But this is just the rule. It says that every time one of these units dissociates, breaks apart, I get 1 magnesium 2 plus 2 hydroxides. This should be something that you can look at and write down based on your Chem 105 knowledge. But again, at the instant that the magnesium hydroxide is put in the solution of sodium hydroxide, we have an excess of magnesium hydroxide, we have a lot of it, but none of it's dissociated. So my initial concentration of magnesium is 0, and then this is the actual concentration of hydroxide. Again, the 2 is not going to play a role. These are actual concentrations, these are actual amounts of the material. This right here, this column is going to tell me how much magnesium 2 plus is present. This column tells me the actual amount of hydroxide that's present in solution. Well, I'm not at equilibrium for the reasons we've discussed. I can't have 0 concentrations at equilibrium, so I have to have some dissociate here. So one of the things that we notice is, even though this is a tiny number, even though the dissociation here should be just minuscule, and it will be, it's going to be absolutely tiny, there still has to be some at equilibrium. And so that's what we're really figuring out, is what is this tiny concentration going to be? Okay, so I'm going to say plus x here, and now I'm going to have 1.5 plus what? Well, plus 2x, because every time an amount x of the magnesium is formed, an amount 2x of the magnesium hydroxide is formed. And again, this table right here is giving me actual concentration. So I increased the concentration of the magnesium by x, so that means that I've increased the concentration of the hydroxide by twice that amount. Again, we know that we have an excess of magnesium hydroxide, so I have some left. And again, I can be vague here because the concentrations of pure solids don't appear in the equilibrium expression. I just need to know I have some of it, and I've satisfied my conditions here for the problem. But 0 plus x is x. Oh, actually, that shouldn't have been there, right? Okay, so my change, I apologize, I had added everything together. My change was, let's see, some of this dissociated, some of it's lost. I get an amount plus x here, an amount plus 2x here. And then now we come to the final sum, 1.5 plus 2x. I apologize if that freaked anybody out. But yes, an amount x is formed by this dissociation, and an amount 2x here is created. And so now I'm going to write down KSP is equal to, but before I do that, let's talk about what we think will happen here. Again, I'd ask the class, big number or small number? Everybody says small number. Yeah, it's a really tiny number. So do I expect x to be big? No, I expect x to be really small. I don't expect very much magnesium hydroxide to dissociate, so I expect this to be a small number. Now, it's okay for this number to be small. It can be small by itself, but if I take 2 times a very small number, I still have a very small number. And so compared to 1.5, this is probably going to be really insignificant. So I'm going to guess that 2x is much, much less than 1.5. So again, this is a comparison game. I can't neglect x here because I'm not comparing x to anything. But I can look at these two numbers and I can say, I'm expecting x to be really small. So twice of x is still going to be really small. I expect this to be much, much less than 1.5. Therefore, both as a convenient and because I don't have very many sig figs in my problem, I'm justified, in fact even compelled, to neglect x right here. And so what I'm going to write here is KSP is equal to, let's see, the concentration of the magnesium 2 plus times the concentration of the hydroxide. And this is equal to x times 1.5 squared. And this doesn't look like it'll be very hard to solve. I'm just going to take the value of KSP, I've got it right here, divide it by 1.5 squared, and that should give me x. Let's see what I have. So I have 1.8 times 10 to the minus 11, and I'm going to divide that by 1.5 squared, and I get 8 times 10 to the minus 12. So let's see, what were we asked for? What is the concentration of the magnesium 2 plus? Well, I solve for x. X is the concentration of the magnesium 2 plus. And so it looks like we have a solution to this problem, and it is indeed 8 times 10 to the minus 12. Did we make a good approximation here? Yeah, it's an amazing approximation. It was outstanding. 8 times 10 to the minus 12, what's 2 times that? Well, that would be, what, 1.6 times 10 to the minus 11? How does that compare to 1.5? It's tiny, tiny, tiny. It's like, it's 1 penny compared to $1 billion. In fact, it's even smaller than that. The penny just doesn't matter compared to the $1 billion in anybody's accounting. Okay, so clearly this is going to be less than 5% of this. We could check it. We could say, let's see, is 2 times 8, I'm leaving off the sig fig, times 10 to the minus 12, divided by 1.5 times 100%. Is that really less than 5%? So is it less than 5%? And we can all kind of do the math. And we can say, yeah, it's a lot less than 5%. But now here's a question for you. What if I thought that this was going to be small, and it turns out to not be less than 5% of this? What do we do? And the answer is we have to solve the problem not neglecting x. So we have to put all of this in for here. Oh yeah, I forgot to square that right here. Okay, yeah, so we'd have to put all of this in here. And usually that involves solving a quadratic or sometimes worse, and there will be times when we have to solve a quadratic in this class. But again, if my approximation is not good, if this number is not less than 5% of this number, then all I figured out by solving the problem is that I can't neglect x, and then I have to solve the problem. Okay, let us move on. So what do we see? We again see here about neglecting x. This is an important concept you should know. Absolutely, it's mathematically justified. It's a great convenience in solving many of these problems, and you should definitely know how to approach problems this way. And sometimes what you're going to find is that if you don't neglect x, there's just no easy way to solve these. And in fact, I don't want to belabor the point too much, but if you were to take this and put it in here, all of a sudden you've got a quadratic, and then you multiply that by x, and you've got a cubic system, and so you've got something that's hard to solve mathematically. Okay, so this is now an important question for anybody doing inorganic solution chemistry, and that is, if I have two solutions and I mix them together and I have ions in both solutions, will a precipitate form? And of course, a precipitate means that this is stuff that drops out of solution. And when you have KSP values that are very, very small, you realize that you can't have very high concentrations of ions in solution before a precipitate will form. And so if I, again, take 2 ions and dump them in solution, and the concentrations are fairly high, and the KSP value for the corresponding salt is very small, that means that the reaction is probably going to have to go to the left for the system to reach equilibrium. And again, a solid's going to crash out, and that's the precipitate right there. So how would we determine whether or not a precipitate forms? And the answer is we would go to our friend Q, the reaction quotient. And so once again, if I have an equilibrium expression, at equilibrium I can write down this right here. KSP is equal to the concentration of A times the concentration of B minus, A plus and B minus. But Q applies at any time under any set of conditions. So we could say at the instant that I mix my two solutions together, I have a concentration of A plus and a concentration of B minus. And now how does Q compare to KSP? If Q is too big, what does that mean? Well, that means that the reaction has to go to the left because Q has to get smaller, and that means a precipitate will form. If Q now is less than KSP, that means the solution could carry more of the ions, and so if the material were available, the reaction would want to go to the right. So once again, let's see, if Q is equal to KSP, the system is at equilibrium, and the solution is saturated. There's no more ion carrying capacity in the solution. If Q is less than K, that means to get to equilibrium, Q has to get bigger. How would Q get bigger? Well, these concentrations would have to increase. That means that more material would dissociate. And so if it were available, it would dissociate. I could put such a small amount of this material in solution that it will all dissolve, and there will be no precipitate left. And so I won't have an equilibrium system in this sense because I don't have enough material. The solution, the carrying capacity of the solution is high enough that these ions will dissociate, and even more could dissociate. If, however, Q is greater than KSP, and so if Q is greater than KSP, this means that the product of these two concentrations is too high, and so how do we get to equilibrium? Well, the concentrations go down. That means that the reaction goes to the left, and a precipitate forms. And so this material crashes out of solution, a precipitate forms, until these concentrations are what concentrations? And the answer is until they're the equilibrium concentrations. And then, of course, Q is equal to KSP. So systems are always trying to move to equilibrium because that's the lowest energy position for a system. Here's a little chemistry humor. I like this joke. I saw this a while ago. If you're not part of the solution, you're part of the precipitate. So I will leave you with that thought, and then we will move on to the next lecture. It looks like we've got probably on the order of about 20 minutes or so, 25 minutes to work on the next lecture. So let's do that. Let's move on to 19, lecture 19. Okay, here we go. Yep, hope you're doing your reading for class when we have class. Let's see, KSP for barium sulfate is this, small number. A solution is prepared that is initially 5 times 10 to the minus 12 molar in barium 2 ion and 3 times 10 to the minus 3 molar in sulfate. What will happen? Okay, so this is now an application of the concept that we just learned, and so we have barium sulfate, and we all should recognize that it can dissociate as follows, where I get Ba2 plus SO4 2 minus. This is Chem 105 type material. We understand that the sulfate ion works as a unit, and then we've got barium 2 plus and all that. So if I had equilibrium concentrations, I could write KSP is equal to the product of these two concentrations, but I don't know if I am or not. I made a solution. Initially, the concentration of barium is this, and the concentration of sulfate is this. So am I at equilibrium or not? I don't know, but I can certainly calculate a reaction quotient, a Q value, for this chemical expression. And so I have Ba2 plus times SO4 2 minus is equal to 5, I'll leave off the other sig fig, times 10 to the minus 12 times 3 times 10 to the minus 3. And if I'm not mistaken, that's 1.5 times 10 to the minus 14. And so Q now, this value right here, is less than KSP. what that means is that to reach equilibrium, to get to equilibrium, Q has to get bigger, because Q is going to keep getting bigger in this case until it gets to KSP, and then we're at equilibrium. So that means more material could dissociate. If I don't have that material to dissociate, of course these ions just sit in solution, they swim around happily, but this equilibrium is not operative because I don't have any of this in place, and the solution could carry more of these ions, more of the barium 2+. So the answer is a precipitate will not form, and the answer it will not form is because Q is less than KSP. Okay, so you kind of can see what's going to happen. Now we're going to consider the other possibility right here. And so we've still got barium sulfate, so let's write down quickly the dissociation for this salt. And so I have Ba2 plus SO4 2-. Both of these are aqueous ions, so I won't write it for both of them, but I could write AQ, which stands for aqueous. Aqua means water in Latin, so that's where we get these. These are hydrated or solvated or whatever, however you want to say it. So in any case, we have a solution that's prepared that is initially 2 molar in barium, in the barium ion, and 1.5 times 10 to the minus 3 molar in the sulfate, so that's still a fairly high concentration. What will happen? And so now let's see. Let's assume that we don't recognize immediately from these numbers what's going to occur, and let's say, well, okay, so I've got this solution. It was prepared with these concentrations initially of these ions. Let's calculate a Q value to try to determine what will happen. So Q is equal to the concentration of barium times the concentration of sulfate. These, again, this Q expression applies at any time under any set of conditions, and so now I'm going to put in 2 times 1.5 times 10 to the minus 3, and this gives me 3 times 10 to the minus 3, and we say, oh heavens, this is so much bigger than this right here. So this is much, much bigger than 1.1 times 10 to the minus 10. So now our scenario is that Q is too big. I've got too many of these ions, and how can Q get smaller? Why does Q want to become smaller? It wants to become smaller because it wants to become KSP. I'm not at equilibrium under these conditions. I have to get down to KSP. Q has to get smaller. How does Q get smaller? These concentrations go down. What does that mean? That means a precipitate will form. To drop these concentrations in solution, these combine, drop out of solution, form the salt. Yes, a precipitate forms, and a precipitate will form because Q now is greater than KSP, and if we wanted to, we could even say it's just much, much bigger than KSP. So certainly a precipitate is going to crash out of this solution. So I don't think that should be here. That's not. I think I just copied and pasted this from the previous slide. So that last comment. Let's see. Yeah. So I think what happened was I must have changed. I think what I did was I just changed the numbers, as I sometimes do on these problems, from year to year, and that shouldn't be here, because certainly more of these ions can't be present in the solution without a precipitate forming. So that comment is incorrect. So let's go on to the next problem. So let's see. And there's a reason that we're just kind of solving problem after problem, because I want you guys to see how it is that we approach these problems, because again, this is going to be an important part of the test, but it's also an important part of what follows. If you understand this, then you're going to understand acids and bases, and that's another important part of the class. And so to be quite, I don't want to be overly blunt, but if you don't understand this, if you fail to understand these concepts that we're talking about, you're going to struggle in the next unit, and then we're talking about a fairly large portion of the material in the class that maybe you're not getting, and that's not so good for your performance on the upcoming tests. Okay, so let's see. We have a problem. We have a concentration and we have a volume. So 0.93 liters of 0.22 molar calcium nitrate is diluted by addition of 0.53 liters of water. What is the final concentration of Ca2+? So there are a few things that we need to think about with a problem like this. We see this salt, and we see it's a nitrate salt, and we remember that all nitrate salts are soluble in water. Whew, okay, so that's really convenient, really cool. I've got this nitrate salt, complete dissociation in water, and we should see what happens. I'm going to get a Ca2+ and 2 nitrates. Now what I've done is I've added, though, 0.53 liters of water to this volume right here. And one of the things that we're going to assume in this class is that is that if I add this much volume to this volume, that they're purely additive, and that there isn't some either expansion or contraction of the solution that takes place when when I do. There isn't kind of this change in volume that takes place with mixing, and that certainly happens with certain solutions, like if I mix alcohols with water or things like that. But we're just going to assume that they're purely additive, and probably not a bad approximation right here. But we're also going to remember a formula that you've probably seen before, which is that in a situation like this, the initial concentration times the initial volume is equal to the final concentration times the final volume. And now, kind of, what does this mean? Well, an initial concentration is the number of moles divided by the volume initially right here, and I'm going to multiply that by the initial volume. And this is now, in a situation like this, I would ask the question, did you change the amount of calcium nitrate that you had in this solution when you added water? And the answer is, of course not. We had this solution of calcium nitrate, but we just dumped in some water. And so the number of moles of calcium nitrate, the number of moles of calcium 2+ and nitrate ion, none of that's changed at all. We have the same number of moles of this. It's just that we've diluted it. So the concentration's gone down, but we have the same number of moles. And so that's why I'm going to put moles here, because it's the same number of moles in a final volume times the final volume. And we can see that volumes are going to cancel on both sides. And so all we're really saying is that the moles before is equal to the moles after. And again, that's certainly a true statement if all we're doing is adding water to a solution like this. And so that's why this formula, it's convenient and all that, and that's why the use of this formula is justified here. So we're asked for a final concentration of calcium 2+. And so how am I going to solve this? Well, let's do the algebra. It's simple algebra, right? So we have Ci times Vi divided by Vf. And again, we just solved this formula for the final concentration. And so let's see, the final concentration is equal to the initial concentration, which was 0.22 moles per liter, times the initial volume, which is right there, which is 0.93 liters, divided by the final volume. And what's the final volume? The final volume is the initial volume plus whatever we added to it. So we have 0.93 liters plus 0.53 liters. And if we throw this to our calculators, we should get the right answer. So I took 0.22 times 0.93, and then I'm going to take 0.93, and I'm going to add 0.53, and divide that, and I get 0.14 molar. And so it is 0.14 molar. You can write that here. In fact, I got 0.140 if you want that extra sig fig. But you see that I was actually kind of a little bit tricky right here. It would be hard to guess here, and I will do this maybe on a future exam as well. Just make sure that you can get the right answer here and put in the numbers correctly. But in any case, use of this fairly simple formula, and it will come in handy. Okay, what time are we dealing with here? Great, we've got about 7-8 minutes left. Let's at least get into this problem. And now what we're introducing is a different type of table in addition to an ICE table. And we're going to call this a BCA table, before change after table. We will run this table before an ICE table, and we're going to run this table when a precipitate will form. And so what we have here is we have lead iodide. So this is another important problem, and this is a more involved problem. It's a little bit more complicated. It involves everything we've learned plus some new concepts, or at least some mechanics are new. Maybe the concepts aren't entirely new, but the mechanics of how to solve the problem are new. So let's see. I'm going to write down the dissociation. I know enough inorganic chemistry that I can look at this and I can see how it's going to dissociate. And now I'm mixing, oh heavens, what am I doing? I've got 1 liter of 1 molar lead nitrate and 1 liter of 1 molar potassium iodide. And okay, so I can see that I'm going to have pretty high concentrations of these two, even when I mix the two solutions together. And it's certainly looking to me like a precipitate will form. How would I know that? Well, the KSP value is just so small here. And in fact, maybe what we should do is we should figure out what the concentrations of these ions are going to be in this solution right here. Now, the equilibrium that I care about is this one right here. I know that all nitrate salts are soluble, and so I'm going to make some nitrate here, but the nitrate just kind of sits there and swims around. It's a spectator ion. And I know that potassium salts, all potassium salts are soluble too, and so I'm going to make this solution. The potassium is just going to kind of swim around. And in fact, maybe a good place to start this problem, since I'm asked for the concentrations of all the ions, is to say what are the concentrations of nitrate and potassium, because as spectator ions, they're not participating in this equilibrium, and I wouldn't expect them to cause any precipitation or anything like that. These types of salts are soluble. These types of salts are soluble. So again, yeah. So these are kind of spectator simple species. But let's see. I have 1 liter of 1 molar. This is 1 mole per liter, and so this tells me that I have 1 mole of Pb2 plus. And now by stoichiometry, every time, well, let's just actually write it out. Let's see, every time one of these dissolved, I get 1 Pb2 plus 2 nitrates. So that means that if I have 1 mole of lead 2 plus in solution, that means I have 2 moles of nitrate. And now what I need to do to get a concentration is I need to say what's my total volume. Well, I had 1 liter of this solution plus 1 liter of this solution, so my total volume is 1 liter plus 1 liter is 2 liters. And over here I have 2 liters of this. So this tells me that the concentration of nitrate in solution is 2 divided by 2 is 1 molar. So that right here, that is the concentration of nitrate. So I've got that right there. 1 molar should be my concentration of nitrate. It's a spectator ion. It does nothing. Now, I have calculated the concentration of Pb2 plus, and that looks like it's going to be 1 over 2, which is 1/2, 0.5 molar Pb2 plus. So I'm going to write that down right here, 0.5 molar. And the reason I'm going to put it here is because we're starting to create a table of initial concentrations and all that. But certainly, again, with this type of equilibrium and the KSP value as small as it is, I just don't have, I'm just confident that this is not going to be my final concentration of lead. Some of it's going to dissociate. Okay, so let's come over here and deal with this dissociation. Of course, we get K plus I minus. I have 1 liter times 1 mole per liter. This is, I have 1 mole of this, and I have 1 mole of this. But my final volume is what? Well, I started with 1 liter of this solution, 1 liter of this solution, 1 liter of this solution right here. That's a total of 2 liters. We did the same argument here. So I have 2 liters here, and I have 2 liters here. And that says that the concentration of this spectator ion right here, this calcium 2 plus, I'm sorry, this calcium plus, sorry about that, this is equal to 0.5 molar, and it's a spectator. It just sits there. It does nothing. I don't need these in square brackets. Sorry. That's not correct. It is a little, again, jet lag's a real thing. So in any case, what is our concentration of the I minus? It's also going to be 0.5 molar. So I think we've got all of that correct. But now I've got a concentration of the nitrate. So I guess if I want square brackets, the concentration of nitrate is 1 molar. The concentration of K plus, both of these are spectator ions. K plus concentration 0.5 molar. And now I have these two equal to each other. And initially I have none of this. So what we're going to do is we're going to create a BCA table. And the way I know I need a BCA table is because I know a precipitate is going to form here. The way I know a precipitate is going to form here is because I could take this concentration and multiply it by this concentration squared, and the number is going to be much, much greater than this. A precipitate has to form. This reaction has to go backwards for me to even have a chance to go to equilibrium. And what I do in a BCA table is I let the entire back reaction take place. I'm going to assume that the reaction goes all the way the other way. In other words, I'm going to let everything that can react. And I'm going to do this, well, and it's not going to be a bad approximation. Of course, I'm going to end up with one of these concentrations as 0, which isn't quite true, but I'm going to take it all to the left because this number is so small. This number says I can't have these types of concentrations, and one of these concentrations is going to end up being just tiny. And so I'm going to end up with a concentration here as close to 0, and that's going to be a pretty good approximation. So the BCA table gets you pretty close to the truth, and then the ice table is just the finishing touch to it. So because a precipitate is going to occur, I'm going to let the precipitate occur through this BCA table. Before, my starting point is this. Now I'm going to ask you a question. Do we have enough iodide for all the lead to precipitate? And the answer is no, because let's see, I need 2 iodides for every lead. And so that means that if my concentration of the lead is 0.5 molar, the concentration of the iodide would have to be 1 molar for there to be enough for all the lead to precipitate. So that can't happen. Do I have enough lead for all of the iodide to precipitate? The answer is yeah, of course I do, because let's see, I just need, for every 2 of these, I need 1 of these, and so I need 0.25 molar lead for all of the iodide to precipitate. So again, because my KSP value is so small, because this reaction has almost no tendency to occur because I have high concentrations here, I'm just going to let it all go backwards. And remember, we can approach equilibrium from either direction, from the left or from the right. I can take it all back mathematically, and this is just a mathematical game to make my life easier. It doesn't seem like it's easier, but actually it is. I can let it all go backwards and then just bring it forward just a tad, just a tiny bit to finally reach equilibrium. Again, and this was one of the principles we talked about that may not have really registered when we emphasized it, but this is where it comes into play. I can let the system mathematically go back and then bring it forward a little bit. It doesn't matter the direction that I approach equilibrium. It's valid either way. Okay, so I'm going to let my change be all of this. Again, this is kind of a mathematical exercise, but it's the right way to solve this problem. It makes sense. It's pretty close to the truth. And because, again, I write actual concentrations here, this is my rule telling me how, if one of these dissociates, I get 1 of these and 2 of these and all that. But the actual concentration of iodide here is this. The actual concentration of lead here is this. Iodide concentrations here. Well, anyway, I get some now. Some precipitate forms. So I have a reaction here. I'm taking the reaction to the left. And so I still have some here after this change. So this is before my change. This is the change. This is after. And now I get 0.25 molar, and I have 0. So the BCA table is incredibly important. It tells us what happens when we have a precipitate, or when we know a big change is going to occur. And heavens, a big change is going to occur here. Look at the size of this tiny, tiny number, and look at the high concentrations here. A precipitate just has to form. We could see this by calculating Q. I know I'm running a little bit over time, but consider this to be part of the next lecture. I'll let the next lecture be a little bit shorter, but I want to finish this problem. This is a really important problem. Now, it turns out that the last line of a BCA table is the first line of an ice table. And so now what I'm going to do is I'm going to tweak things. Did pretty much all of the iodide precipitate out? Yeah, it's a good approximation. We'll see it's a really good approximation to have 0 here. But I can't possibly be at equilibrium here, so now I'm going to allow the system to just tweak a little. And so now I'm going to go the opposite direction. So this always happens in a BCA table. We go one direction, and then we're going to let things just come back just a little bit the other way just to get to equilibrium. So now I'm going to let some dissociate. And when that happens, I'm going to get an amount plus x here and plus 2x. Every time one of these dissociates, I get one of these and two of these. That's reflected here. And of course I have some left. We just made a lot of precipitate. And so I get 0.25 plus x, and I get 2x. But now I look at these two numbers and I say, really small number here. I don't expect x to be big. In fact, I expect x to be really, really small, much less than 5% of this. So again, this should be much smaller than this. I'm always comparing these two numbers to each other. This should be really tiny compared to this. This should be less than 5% of this. We can go back and check our approximation, and we should when we're done to make sure that this is less than 5% of this. But for now, let's just neglect this. It's mathematically justified, and it makes our lives much better, much easier. So I'm going to say KSP is equal to the concentration of Pb2+. When I have a lot of writing on the screen, I guess, I don't know if it's the computer memory or whatever it is that, let's get rid of that, kind of has a hard time with the writing here with my stylus and this little pad that I write on. But in any case, let's see, KSP is equal to the concentration of Pb2+, and I guess we could have just put in 0.25 right here, times 2x squared. So the concentration of I minus is 2x here. I'm going to square it because of this rule. KSP is 8.5 times 10 to the minus 9. And so let's see, let's calculate, and let's figure out what 2x is. You might say, why are you doing that? Why are you not solving for x? And the answer is because 2x actually is the concentration of iodide right here, and I need the concentration of iodide. So, and we could, of course, then take half of this and see if then x is going to be less than 5% of 0.25. But let's run the numbers right here. Let's see, I'm going to take this divided by this, take the square root. So I have 8.5 times 10 to the minus 9 divided by 0.25 square root, and I get 1.8 times 10 to the minus 4 molar. And so half of this is going to be 0.9 times 10 to the minus 5. That's certainly less than 5% of this. You could do the little thing we did before, take this divided by this, multiply by 100%. Is that less than 5%? The answer is yeah, it's a lot less. So we're very justified in neglecting x here. And that means that the final concentration of the lead 2+ to a good approximation is equal to 0.25 molar, and the final concentration of the iodide is equal to this. And let's see if we got this right. So let's see, the concentration of lead 2+ is 0.25 molar. The concentration of I- is 1.8 times 10 to the minus 4 molar. The concentration of the potassium, let's see, is 0.5 molar. That's what we've got. The concentration of the nitrate is 1 molar. So we solved the problem right. And I just want to take a minute as we conclude this lecture to just say this is fairly involved, but we're going to see this on multiple occasions going forward in this class. What do you do when there's going to be a big change in your system, like a big reaction is going to take place, like a precipitation or something like that? Run a BCA table and then run an ice table. You see how the BCA table got us most of the way there? You know, the concentration of the lead 2+ that we got out of the BCA table ended up being the concentration in solution. Oh, that doesn't look like a very good M, does it? There, that's supposed to be an M. So the concentration of the lead 2+ that we got out of the BCA table is the final concentration of lead 2+. And then we got 0 at the end of the BCA table for the iodide concentration, and this concentration is pretty low, so maybe not that far from 0. So the BCA table actually got us nearly to the finish line, and then we just had to tweak it a little bit with an ICE table. So the application of a BCA table followed by an ICE table. The last line of a BCA table is the first line of an ICE table. And remember that we always go in opposite directions here. So for the BCA table, it's a big change. In this case, we went to the left and then just a small amount to the right. There will be times where we could run a BCA table where instead we're going to be taking things forward and then going back just a little bit. So same type of principles apply, but this is how we solve this more advanced problem. I wish you all the best, and look forward to being back, because I sure love to be up in front of everybody and having a more dynamic interaction than this. But I hope that this is helpful, and I think that one of the things that's valuable here is your ability to be able to replay these lectures, and I've heard from multiple students that is kind of a benefit of having these lectures, is again the ability to watch and re-watch them to make sure that you understand each step in solving this problem. So I guess that's it, and I will conclude this lecture. So this was 10 minutes more than a normal lecture, and so I'll try to make the next one a little bit shorter. Thanks. See you. Bye.